Imagine you are drifting, untethered, in the profound silence of the great void. Above you, the sun hangs like a violent celestial furnace, a ball of plasma so intense that its core screams at 27 million degrees. Even from 93 million miles away, its light is blinding, a raw outpouring of 384 septillion watts of energy every single second. You are staring directly into the most powerful source of heat in our corner of the galaxy, a fire so vast it could swallow a million Earths and barely notice the meal. Yet, as you float there, bathed in that golden radiance, something impossible begins to happen. Your blood doesn't boil. Your skin doesn't blister. Instead, you begin to freeze. Just inches from your visor, in the shadows where the light cannot reach, the temperature has plummeted to 455 degrees below zero. You are witnessing a cognitive dissonance that defies every instinct we've developed, living on a warm, blue marble. We are taught from birth that if you stand near a fire, you get warm. We see a sky filled with billions, trillions, and quadrillions of stars, each one a sun, each one a nuclear engine of unimaginable fury. And our intuition tells us the universe should be a literal hellscape of heat. If the night sky is lit by more fires than there are grains of sand on every beach on Earth combined, then why is the space between them so bone-chillingly cold? The answer most people give you is that space is a vacuum, and a vacuum has no temperature. They tell you that heat needs matter to travel, and since space is empty, the heat simply doesn't stay. This is the explanation you'll find in every textbook and every standard documentary. It's a clean answer, a safe answer, and it is almost entirely incomplete. It misses the deeper, more unsettling truth about the nature of our reality. It fails to address the radiative isolation paradox, the fact that you aren't actually standing in a cold void, but in a sea of invisible fire that refuses to touch you. To understand why you would freeze while staring at the sun, you have to realize that our entire human experience of warmth is a localized anomaly. On Earth, we live in a world of constant touch. We are surrounded by 25 quintillion molecules in every cubic meter of air, all of them jiggling, vibrating, and bumping into us. When the sun hits our atmosphere, it's like a bell being struck. The energy vibrates the molecules, and those molecules vibrate against our skin. We feel the heat because the universe is rendering it for us through the medium of matter. But out there, in the deep black, the rendering stops. Think of the universe as a vast, high-efficiency simulation. In the voids between the stars, there is often only one single atom per cubic meter. For all intents and purposes, the universe is unrendered. The energy is there. It is screaming past you at the speed of light, but because there is nothing for it to hit, the energy remains dark. It is a ghost. You are standing in a room filled with the loudest music imaginable, but because there is no air to carry the sound, you die in total silence. This is the true nature of the cosmic cold. It isn't an absence of energy. It is a systematic isolation of it. This brings us to a terrifying realization that most scientists are hesitant to say out loud. The cold is not the exception. The heat is. We look at the stars and see them as the dominant features of the cosmos, but they are actually tiny, fleeting anomalies. If you were to take all the heat from every star in every galaxy and spread it evenly across the universe, the temperature would barely rise above absolute zero. The cold isn't just winning, it has already won. We often frame the universe as a place of creation and light, but the entropy dominance theory suggests something much more somber. The sheer, overwhelming cold of space is a reminder that the default state of the universe is balance, a cold, dead equilibrium. The stars we see are like the last few sparks flying off a log that has already turned to ash. They are beautiful, yes, but they are temporary. They are the leftovers of a Big Bang that happened 13.8 billion years ago, a singular moment of heat that has been stretching and thinning ever since. When we ask why space is so cold, what we're really asking is why we are so lucky to be warm. We are living inside a rare, protected bubble. Our atmosphere acts as a heavy blanket, a thermal shield that captures the ghost energy of the sun and forces it into a form we can feel. Without that blanket, we would realize that the daylight we love is actually a lethal stream of radiation passing through a frozen graveyard. The Parker Solar Probe, one of the most daring pieces of machinery ever built, experienced this paradox firsthand. In 2021, it flew within 6.5 million miles of the sun's surface, entering the corona, where temperatures reach millions of degrees. Its heat shield was hammered by enough radiation to melt solid steel, glowing at a white-hot 2,500 degrees Fahrenheit. And yet, just a few inches behind that shield, in the artificial shadow it created, the spacecraft's delicate instruments were operating at nearly 240 degrees below zero. Think about that. You can be close enough to the sun to feel its literal breath, and yet, if you step just 1 foot into the shade, you are instantly transported back to the baseline temperature of the Big Bang. There is no middle ground in the cosmos. There is no room temperature in the stars. There is only the inferno and the ice, and the line between them is as thin as a shadow. This is the mystery we are going to unravel. We aren't just going to talk about conduction and convection. We are going to explore why the universe seems to be hiding its energy from itself. We are going to look at the Boomerang Nebula, a place so cold it actually robs heat from the Big Bang's afterglow, and we are going to ask the question that changes everything. The right question isn't, why is space so cold when the stars are so hot? The right question is, in a universe that is almost everywhere and almost always unimaginably cold, how does a world like ours even exist? We are the anomaly. We are the glitch in the frozen simulation. And as we peel back the layers of this cosmic paradox, you might find that the darkness between the stars isn't just empty. It's waiting. It's the final state of everything we know, and the stars are merely the final desperate protests against an eternal, silent winter. Welcome to the deep freeze of the infinite. This is the story of the fire that couldn't warm the world. To understand the bone-chilling reality of the cosmos, we first have to dismantle a lie your senses have been telling you since the day you were born. We treat cold as if it were a substance, a mist that rolls in, a force that bites at your skin, something that can be added to a room. But in the eyes of physics, cold does not exist. There is no such thing as a cold particle. There is only the presence of energy, or its profound, terrifying absence. When we say space is cold, we are actually describing a failure of movement. Think about what temperature really is. It isn't a magical quality inherent to the air. It is a speedometer. Every single thing you have ever touched is made of atoms, and those atoms are never, ever still. In a hot cup of coffee, the molecules are screaming, crashing into each other like a mosh pit at a rock concert. In a block of ice, they are slow dancing, shivering in place, but still moving. Temperature is simply the measurement of that kinetic frenzy, the average speed of the dance. On Earth, you are never truly alone. You are submerged in a thick, invisible ocean of matter. Even in a room you think is empty, every cubic meter of air around you is packed with 25 quintillion molecules. That is a 25 followed by 18 zeros. You are being pelted billions of times a second by tiny microscopic bullets of nitrogen and oxygen. When you step into the sunlight, the sun's energy hits these molecules and sets them vibrating. They, in turn, slam into your skin, transferring that motion to your own atoms. You feel warmth because you are being hit by 1 trillion tiny hammers. Now, look at the void. In the vast, silent corridors between the stars, the math of reality breaks. If you were to take that same cubic meter of space, the same volume that holds 25 quintillion molecules on Earth, and look at it in deep space, You might find only one single atom. Sometimes you find none at all. The density of the universe is so low that it is essentially a perfect vacuum. This is the anatomy of nothing, and this is where the mystery deepens. If temperature is the speed of the dance, what happens when there is no one on the dance floor? Technically, it is a scientific trap to say that space is cold. A perfect vacuum cannot be hot or cold because there is no matter there to hold the energy. It's like asking what the color of a sound is. The question itself is built on a category error. If you placed a thermometer in a truly empty void, the thermometer would have a temperature, but the space around it would not. This is why some physicists argue that space isn't cold, it's just nothing. But nothing has a very specific and lethal consequence for anything that dares to enter it. In this unrendered environment, the energy from those billions of stars becomes a ghost. Imagine a high-end video game where the engine only renders the lighting and the physics in the exact spot where the player is standing. The rest of the world exists as raw code, but it has no physical form. Space behaves exactly like this. The radiation from a billion suns is streaming through the vacuum, but because there is no hardware, no atoms, to process that energy, the heat never manifests. It stays in its raw electromagnetic form, invisible and unfelt. This is what we call the passive empty state. Space is not actively trying to freeze you, it is simply indifferent. It is a vacuum so powerful that it doesn't just suck out your air, it sucks out your motion. On Earth, if you pour a hot cup of tea, it stays warm for a while because the air molecules around it are relatively slow, and they steal the heat through contact, a process we call conduction. But in space, there is nothing to touch. You might think this means you'd stay warm forever, but the universe has a much more efficient way of robbing you. Every object in the universe, including your body, is constantly screaming away its energy in the form of infrared radiation. On Earth, the thick atmosphere acts like a mirror, bouncing some of that energy back or providing a warm cushion of air to slow the loss. In the vacuum, there is no cushion. There is no mirror. Your body heat simply radiates away into the infinite blackness at the speed of light, and nothing, absolutely nothing, comes back to replace it. This is the deeper lore of the cosmic baseline. We often think of the sun as a bonfire that should heat the whole room of our solar system. But space isn't a room, it's a backyard the size of a galaxy. Expecting the sun to heat the vacuum of space is like lighting a single match in the middle of a Category 5 hurricane and expecting it to keep the entire forest warm. The scale of the nothingness is so vast that the somethingness of the stars is drowned out. Consider the sheer distance between these furnaces. Our closest neighbor, Proxima Centauri, is 4.3 light-years away. If you hopped in a car and drove 60 miles per hour, it would take you 48 million years to get there. Between us and that star is a gap of nearly 25 trillion miles of nothing. One atom here, one atom there. In a system that big, heat doesn't spread, it dissipates. It obeys the inverse square law, which dictates that energy doesn't just fade, it collapses. By the time the light from a distant star reaches a point in deep space, its ability to actually move an atom, to heat it, has been diluted to almost zero. This is why the unrendered theory is so compelling. It suggests that the universe is a system of isolated render zones. Inside an atmosphere or near a star, the density is high enough for the heat software to run. The atoms can bounce, the energy can transfer, and warmth becomes a reality. But the moment you step outside that zone, you are in the code. You are in a place where the rules of heat no longer apply because the medium for those rules has vanished. We are left with a universe that is a graveyard of kinetic energy. The billions of stars we see are not heating the universe. They are merely points of light in a dark ocean that refuses to be warmed. They are anomalies of motion in a cosmos that is fundamentally still. When you look at the stars tonight, don't just see the light, see the gaps. See the trillions of miles of absolute stillness between them. That stillness is the true face of the universe. The heat we feel here on Earth is a localized glitch, a tiny vibrating pocket of resistance against a vacuum that is trying, with every billion miles of its nothingness, to bring the dance of the atoms to a permanent, frozen halt. But if space is nothing and nothing cannot have a temperature, then why do our most sensitive satellites detect a faint, persistent hum of heat everywhere they look? If the vacuum is truly empty, why is there a baseline temperature of -455 degrees that exists even in the deepest, darkest holes of the cosmos? The answer lies not in the stars we can see, but in the ghost of a fire that went out 13 billion years ago. A fire that created the very nothing we are so afraid of. To understand why you could freeze to death while staring into the heart of a nuclear furnace, you have to understand the three ways the universe moves energy. On Earth, we are pampered by a reality where heat is a social butterfly, constantly jumping from one molecule to the next. But in the cold isolation of the deep black, heat becomes a ghost, and the rules we've spent our lives learning simply vanish. This is the story of blind energy, a world where the most powerful radiation in the solar system passes through the void like a silent, invisible arrow, touching nothing until it finds a target to destroy. First, we have to look at the way our world works. On Earth, heat transfer is dominated by two primary methods: conduction and convection. Think of conduction as the universe's version of physical intimacy. When you place a steel plate on a hot cooktop, you only need to heat one tiny edge, yet soon the entire plate is glowing with heat. This happens because the atoms in the metal are packed together like commuters in a crowded subway. When one atom gets energized, it begins to jiggle and vibrate, slamming into its neighbor. That neighbor then slams into the next and the next, creating a chain reaction of kinetic energy that flows through the material. This requires physical touch, a literal passing of the torch from particle to particle. In the vacuum of space, however, this method is fundamentally broken. Conduction is eliminated because in the great voids between galaxies, there is effectively no one left to touch. When you have only one atom per cubic meter, that atom can travel for billions of miles without ever bumping into a neighbor to share its energy. The chain reaction stops before it even begins. The universe's first method of moving heat is paralyzed by the sheer scale of the nothingness. The second method is convection, which is the engine of our weather and our oceans. Imagine a pot of water on a stove. As the water at the bottom gets hot, it becomes less dense and rises to the top, while the cooler, heavier water sinks to take its place. This creates a circular current that distributes heat throughout the entire liquid. We feel this every time a warm breeze hits our face on a summer day. Convection requires a fluid medium, air, water, or gas, to carry energy from one place to another. But space is a vacuum. There is no medium to carry the current. Without air to circulate or water to flow, convection dies the moment you leave our atmosphere. This leaves us with the third and most mysterious method: radiation. Unlike its cousins, radiation is an outlier. It doesn't need to touch anything, and it doesn't need a medium to travel through. It moves as electromagnetic waves, primarily infrared light, which can cross the 93 million mile gap between the Sun and the Earth at the speed of light through a perfect vacuum. This is the only reason our planet isn't a frozen rock. The Sun releases a staggering 384 septillion watts of this energy every single second, pouring it out in every direction like a torrential rain of fire. But here is where the blind energy paradox begins. If the Sun is constantly bathing the solar system in this incredible amount of radiation, why isn't the space between us and the Sun boiling hot? The answer is as simple as it is unsettling. Radiation does not heat the vacuum it travels through. It only heats objects it actually strikes. Think of a high-powered laser beam in a perfectly clean, dark room. You can't see the beam as it travels through the air. You only see a bright red dot when it hits the wall. The path of the laser remains dark and undisturbed because there is nothing in the air for the light to bounce off of. Solar radiation works the exact same way. It is a stream of dark energy that moves through the nothingness of space without leaving a trace of warmth behind. It is blind because it has nothing to see, nothing to interact with, and nothing to vibrate. Only when that radiation hits something with mass, a planet, a moon, a spaceship, or a lone grain of cosmic dust, does the energy finally render into heat. This is the radiative isolation paradox. We are surrounded by a sea of energy that is permanently isolated from the void itself. The atoms that make up our bodies or our spacecraft are the only things capable of catching this energy. When those solar waves strike your skin, your atoms finally have something to absorb. They begin to vibrate, they begin to move, and for the first time, the code of the sun's radiation is translated into the physical sensation of heat. This explains the brutal binary nature of the cosmos. In our atmosphere, the air acts like a blanket, catching the radiation, distributing it through convection, and moderating the extremes so we don't cook or freeze instantly. But in space, there is no transition. There is no warm air to soften the blow. You are either in the path of the beam, or you are in the shadow. On the sunlit side of an object, like the International Space Station, temperatures can soar to a blistering 250 degrees Fahrenheit as the atoms are hammered by raw radiation. But just a few inches away, in the shadow where the beam is blocked, the temperature collapses to minus 250 degrees. The vacuum itself remains at its baseline temperature of minus 455 degrees Fahrenheit, completely indifferent to the inferno passing through it. It is as if the universe is a theater where the stage lights are at full power, but the air in the room remains freezing because there are no actors on stage to catch the light. The heat we think we know is actually a rare, localized phenomenon that only happens when the universe's energy is forced to interact with matter. This reveals a deeper, more existential truth about the cosmos. We tend to think of the universe as being filled with the heat of the stars, but the stars are actually just pinpricks of interaction in an infinite ocean of unrendered energy. Most of the energy in the universe is simply traveling forever through a void that will never feel its warmth. It is a system of profound isolation. When we say space is cold, we aren't describing a lack of energy. We are describing a lack of hardware. The sun's rays don't heat space because there is simply nothing there to heat. The atoms and molecules that do exist in the deep voids are so rare that even if they absorb a stray photon and become hot, they have no way to pass that heat along to anyone else. They remain tiny, vibrating sparks in a cathedral of silence. So, as the sun continues its violent nuclear dance, releasing enough energy every second to power our entire civilization for millions of years, that energy is mostly wasted on the void. It screams through the darkness, blind and unfelt, searching for a world to wake up. We are lucky enough to be one of the few places where that energy finally finds a home, where the ghost becomes a fire, and where the blind energy of the stars finally opens its eyes. But the moment you step out of our protected bubble, you are reminded that the default state of the universe isn't the warmth of the sun. It is the silent, frozen indifference of the path that leads there. If you were to step outside the airlock of the International Space Station without the protection of your specialized suit, you would confront a reality that defies every sensation you have ever known. In our world, warmth is a lingering presence. When the sun slips behind a cloud or the day turns to evening, the air holds onto the heat like a warm memory. The bricks of your house, the asphalt of the road, and the very air you breathe act as a thermal battery, smoothing out the transition between the fire of the day and the chill of the night. But out there, in the raw vacuum, the universe is binary. It is a world of ones and zeros, of absolute light and absolute darkness, with nothing in between to soften the blow. You are standing on a razor's edge, where one step takes you from a scorching hell to a tomb of ice. This is the shadow contrast, a phenomenon that reveals the true, brutal nature of the cosmos. On Earth, we are pampered by our atmosphere, a thick protective blanket that absorbs, distributes, and retains the sun's energy. But in space, there is no blanket. There is only the radiation and the void. If you held your hand out in the direct path of the sun's rays, the side facing the light would instantly begin to cook. The atoms in your glove would be hammered by raw solar radiation, vibrating so violently that the temperature would soar to 250 degrees Fahrenheit, hotter than the boiling point of water. But the palm of that very same hand, turned away from the light and facing the blackness of the void, would be plunging toward minus 250 degrees. Think about that physical contradiction. In the space of a few inches across the thickness of your own hand, the universe is trying to melt you and freeze you at the same time. There is no room temperature in the vacuum. There is no pleasant breeze to carry the heat from the sunlit side to the dark side. Because there are no air molecules to move, the heat is trapped exactly where it strikes. This is what we mean when we say space is unrendered. Without matter to act as a medium, the energy cannot flow. It cannot circulate. It is locked in a state of radiative isolation, where the sunlit side is a furnace and the shadow is a grave. This isn't a theoretical problem. It is the daily reality for the engineers who build our homes in the stars. The International Space Station is perhaps the most complex thermal machine ever constructed. It doesn't just deal with the cold, it fights a constant high-stakes battle against these two simultaneous extremes. As the ISS orbits the Earth, it travels at 17,500 miles per hour, completing a full circle every 90 minutes. This means that every 45 minutes, the entire football field-sized structure passes from the blinding glare of the sun into the total darkness of the Earth's shadow. Imagine the mechanical stress of that journey. In the sunlight, the exterior of the station is baked at 250 degrees. Metal expands, joints creak, the solar panels drink in the radiation. Then, 45 minutes later, the station plunges into the dark. Within minutes, the temperature of the hull collapses by 500 degrees, bottoming out at minus 250. The metal contracts. The internal heaters scream to life to keep the astronauts from freezing. This happens 16 times every single day. 16 summers and 16 winters packed into 24 hours. For the ISS, the transition between hell and ice isn't a seasonal change. It's a heartbeat. This binary nature of space is most vividly displayed on the surface of the Moon. On Earth, we might have a 40-degree difference between a hot day and a cool night. On the Moon, because there is no atmosphere to act as a thermal buffer, the swings are catastrophic. At the lunar equator, when the sun is directly overhead, the surface rocks are roasted to 250 degrees Fahrenheit. You could literally cook a meal by placing it on a lunar boulder. But walk just a few feet away into the permanent shadow of a deep crater, and you are suddenly in one of the coldest places in the known universe. In those shadows, where the sun hasn't reached for billions of years, temperatures drop to minus 290 degrees, colder than the surface of Pluto. This is why the common belief that space is cold is actually a dangerous simplification. Space is not cold. Space is a vacuum that allows objects to become extremely hot or extremely cold, based entirely on their relationship with light. If you are close to a star, you are in a high-energy environment, but the moment you block that light, you are immediately exposed to the baseline temperature of the universe. There is no middle ground because there is no matter to hold the middle ground. We see this extreme engineering at its peak with the Parker Solar Probe. In 2021, this spacecraft achieved the impossible, flying within 6.5 million miles of the Sun. It was deep inside the corona, the Sun's outer atmosphere, where the environment is an inferno. The front of the probe's heat shield was subjected to a staggering 2,500 degrees Fahrenheit, a temperature so high it would liquefy steel and turn most metals into puddles. This is the absolute extreme of the hell side of the paradox. But look at the other side. Just a few inches behind that white-hot carbon composite shield, the spacecraft's delicate instruments were sitting in a shadow of their own making. In that shadow, protected from the direct hammering of solar photons, the temperature was a chilled minus 238 degrees. Think about the precision of that line. On one side of a piece of hardware, you have the heat of a kiln. On the other, you have the deep freeze of the outer solar system. The only thing separating a molten ruin from a frozen computer is a shadow. This confirms the unrendered environment theory. The energy of the Sun is so focused and so directional that it behaves like a laser. It only exists where it hits. In the shadow of the Parker Solar Probe, the universe doesn't know the Sun is there. The heat software isn't running in that shadow because the radiation has been blocked. This creates a pocket of the void that is just as cold as if it were billions of miles away in the deep dark between galaxies. This leads us to a startling conclusion. Heat in the universe is not a state of being. It is a state of interaction. When we stand on Earth, we feel warm because the interaction is everywhere. The air, the ground, the moisture in the sky all work together to create a cohesive experience of temperature. But out there, the interaction is broken. The universe is a collection of isolated hotspots surrounded by an almost infinite cold. If you were a traveler moving through the solar system, your life would depend entirely on staying within the light, but not too much of it, and avoiding the shadows, but not for too long. You would realize that the daylight we enjoy on Earth is a rare, filtered version of a much more violent reality. Space is a place where you can be burned and frozen in the same breath. It is a place where the simple act of turning your back to the sun can be a death sentence of ice, and turning to face it can be a death sentence of fire. The shadow contrast teaches us that the warmth we feel every day is not the default condition of the universe. It is a fragile, protected exception. We live in the only place we know of where the line between hell and ice has been blurred by the miracle of an atmosphere. Everywhere else, the universe is a brutal binary. It is a place of extremes, where the presence of a single shadow can change the rules of physics. But this raises a final haunting question. If the sun is so powerful that it can melt steel at millions of miles, and if there are trillions of these suns in every direction, why does the shadow always win? Why is the baseline of the universe the minus 455-degree chill of the void, and not the millions of degrees of the stars? To find that answer, we have to look past the light we can see and listen to the faint, ancient hum that fills every corner of the nothingness, the ghost of the fire that started it all. We have spent our journey so far looking at the binary war between the fire of the stars and the shadow of the void. We've seen how matter acts as a translator, turning the ghost energy of radiation into the physical reality of heat. But now we must look closer at the nothing itself. If you were to travel to the darkest, loneliest corner of the cosmos, billions of light years away from the nearest galaxy, in a place where no star has ever been seen, you might expect to find the absolute floor of reality. You would expect to find absolute zero. In the language of physics, absolute zero is minus 459.67 degrees Fahrenheit. It is the point where all motion stops. It is the temperature at which the very atoms that make up the universe cease their dance and become frozen, motionless statues. It is the theoretical end of the line. But here is the deepest mystery of the void. No matter where you go in the universe, you will never find it. Even in the most desolate, lightless pits of the great nothing, the temperature never quite reaches the bottom. Instead, every single cubic centimeter of our universe, from the core of the sun to the gaps between galaxies, is filled with a persistent, ghostly hum. The vacuum is not truly empty, and it is not truly at zero. It has a baseline, it has a floor. And that floor sits at exactly minus 455 degrees Fahrenheit. This is the cosmic microwave background, or the CMB. It is the ambient temperature of existence, a faint uniform glow of radiation that saturates every corner of reality. If space is an unrendered simulation, then the CMB is the background noise of the server itself. It is a whisper from the very beginning of time, and it is the ultimate reason why the universe is as cold as it is today. To understand why this minus 455 degree whisper exists, we have to look back 13.8 billion years to a moment when the entire universe was the exact opposite of what it is now. Before the stars, before the galaxies, and before the vast frozen voids, the universe was a white-hot, opaque fog of plasma. It was smaller than an atom and hotter than the core of 1 trillion suns. In those first few moments, the concept of cold didn't exist. There was only an unimaginable, compressed inferno. As the universe began to expand, it began to cool. But for hundreds of thousands of years, it remained a glowing, searing soup of particles so dense that light couldn't even move. Photons were trapped, bouncing off electrons like pinballs in a crowded machine. Then, at exactly 380,000 years after the Big Bang, something miraculous happened. The universe cooled just enough, down to about 5,000 degrees Fahrenheit, for atoms to finally form. In an instant, the fog cleared. The soup became transparent, and for the first time in history, light was set free. The light from that moment, the literal birth cry of the cosmos, went screaming out in every direction. It was a blinding orange-white flash that filled every inch of the young universe. But as the universe continued to grow and stretch over billions of years, that light changed. This is the secret of the cooling cosmos. As the fabric of space itself expanded, the waves of that ancient light were stretched along with it. Think of a rubber band with a wave drawn on it. As you pull the rubber band, the wave gets longer and longer. In physics, the length of a light wave determines its energy and its color. Short waves are high energy and hot. Long waves are low energy and cold. Over 13 billion years, that original searing hot light has been stretched so much that it has shifted out of the visible spectrum entirely. It has been redshifted into microwaves, low-energy pulses that carry almost no heat at all. What we are feeling when we measure the minus 455 degree baseline of space is the exhausted, stretched-out ghost of the Big Bang. It is the original fire of creation, now so diluted by the expansion of space that it is barely more than a shiver. The story of how we discovered this whisper is one of the most famous glitches in the history of science. In 1964, two radio astronomers in New Jersey, Arno Penzias and Robert Wilson, were trying to use a massive horn-shaped antenna to listen to signals from the stars. But no matter where they pointed the antenna, they kept hearing a persistent, annoying hiss. It was a background noise that wouldn't go away, day or night, summer or winter. They thought it was a technical error. They looked for interference from New York City. They checked for radar from nearby airports. They even found a pair of pigeons nesting inside the antenna and spent days cleaning out what they politely called white dielectric material, pigeon droppings. But even with the pigeons gone and the antenna scrubbed clean, the hiss remained. It was coming from everywhere at once. What they had accidentally stumbled upon was the edge of the visible universe. They were listening to the afterglow of the Big Bang. They had found the baseline of reality. For that discovery, they were awarded the Nobel Prize because they had finally proven that the universe has a history, and that history is one of constant, inevitable cooling. This brings us back to our original paradox. Why is space so cold when the stars are so hot? The CMB gives us the ultimate answer. Space is cold because it is old. We are living in the entropy dominance era of the universe. The heat of the Big Bang has already been spent, stretched across billions of light years until it reached its current state of minus 455 degrees. The stars we see today, those billions and trillions of nuclear furnaces, are not the source of the universe's temperature. They are tiny, localized, reheating projects. They are like small candles lit in a massive frozen cathedral that was once a roaring bonfire. The cathedral is still filled with the faint, cold smoke of that original fire, but the heat is long gone. This is the cosmic baseline, and it is getting colder. Because the universe is expanding at an accelerating rate, the fabric of space is stretching faster and faster. This means the cosmic microwave background is being redshifted even further. Its waves are becoming even longer, and its energy is becoming even thinner. There was a time, billions of years ago, when the background temperature of space was as warm as a summer day on Earth. Back then, you wouldn't have needed a sun to stay warm. The very fabric of the void would have been comfortable. But that era is a distant memory. Today, we sit at 2.7 degrees above absolute zero. Tomorrow, cosmically speaking, we will be even closer to the bottom. This reveals a terrifying existential arc. If the baseline of the universe is a cooling whisper from the past, then the stars are fighting a losing battle. Every second, they pour their energy into a vacuum that refuses to hold it, a vacuum that is actively expanding and diluting that energy into nothingness. The cold isn't just a state of being, it is a direction. It is the destination where the entire universe is heading. Even the coldest natural place we've ever found, the Boomerang Nebula, highlights this process. In this nebula, gas is being ejected so fast that it expands and cools to minus 457 degrees, actually becoming colder than the Big Bang's afterglow itself. It is a preview of the future. It is a place where the rendering of heat has failed so completely that it has dropped below the baseline of reality. When you look into the night sky, you aren't just looking at the light of distant stars. You're looking through a sea of ancient, invisible, and freezing radiation. You are standing in the cooling embers of the greatest fire ever known. The stars are hot, yes, but they are drowning in an ocean of minus 455-degree silence. The invisible energy is there, but it is tired. It is stretched thin. It is the ghost of a birthplace that has become a tomb. And as we move forward into the deeper mysteries of the cosmos, we have to ask ourselves, if the very fabric of space is a cooling remnant of a lost fire, how much longer can the stars keep the darkness at bay? The universe isn't just cold because it's empty. It's cold because it is fading. And we are the witnesses to its long, slow, and silent transition into the final freeze. We have reached a point in our journey where the laws of classical physics start to feel less like set-in-stone truths and more like a set of programmed constraints. We've established that space isn't cold because of a lack of energy, but because of a lack of matter to catch that energy. But if we push this logic to its absolute limit, we stumble into a territory that most scientists are uncomfortable discussing. We enter the realm of the simulation layer. We have to ask a question that sounds like science fiction but behaves like science fact. What if the reason space doesn't feel hot is because the universe simply hasn't bothered to render the heat in the voids? Think about the way a modern high-end video game processes a massive open world. If the player is standing in a forest, the computer calculates the rustle of every leaf, the reflection of light on every blade of grass, and the complex physics of every falling raindrop. But what happens to the mountains on the other side of the map? What happens to the ocean that the player isn't looking at? To save processing power, the computer doesn't render them. They exist in the code as mathematical probabilities, but they have no physical presence. They are dark data. The moment the player turns their head or travels to that location, the system snaps into action, rendering the textures and calculating the physics in real time. When we look at the brutal cold of the vacuum, we are seeing the exact same efficiency at a cosmic scale. Heat, as we have defined it, is the kinetic jiggling of particles. It is the rendering of energy into a physical state. But in the gaps between the galaxies, where there are no particles to jiggle, the universe has no reason to execute the heat command. The energy from the stars, that 384 septillion watts of power, is like raw data streaming through a fiber optic cable. It is moving at the speed of light, carrying the potential for unimaginable destruction, but until it hits a terminal, a piece of matter, it remains in its unrendered state. This is the fringe theory of the unrendered environment. It suggests that the galaxy doesn't just lack heat in the voids, it lacks the very capacity for energy to manifest as anything we would recognize as reality. In this framework, the vacuum of space is the culling zone of the cosmic simulation. By leaving the voids empty and cold, the universe saves an incomprehensible amount of processing power. It only activates the energy where it's needed, where the matter is. Challenge your intuition for a moment. We think of heat as something that exists out there in the world, independent of us. We think the sun is hot, whether we are there to feel it or not. But is it? From a strictly relational standpoint, heat is not a thing you find, it is a thing that happens. It is the result of an interaction between radiation and a substrate. If a star burns in a total vacuum with absolutely no matter within 1 billion light years, is that star actually hot? In our localized experience, the answer is an obvious yes. But in the simulation layer, the answer is not yet. Without matter to absorb the radiation, the energy remains in a state of radiative isolation. It is a wave with no shore to break upon. It is a ghost. In this view, space is not cold because it's empty. Space is cold because it's waiting. It is the raw, uncalculated background of a universe that only comes alive when atoms are present to play the game. This brings us to a radical realization. Our perception of reality is entirely based on a glitch in this efficiency. We are the matter that forces the universe to render. We are the anomalies that turn the invisible data of the stars into the physical sensation of warmth. When you step out into the sunlight on a summer day, you aren't just feeling a pre-existing heat. You are witnessing the moment the universe's dark energy strikes the hardware of your body and is forced to compute a temperature. You are the terminal where the ghost becomes real. But what does this say about the rest of the universe? If 99.99% of the cosmos is a vacuum, then 99.99% of the universe is unrendered. We live in a reality that is fundamentally off. The default state of the cosmos is the dark, silent server room where the power is running, but the screens are all blank. The heat we see in the stars and feel on our skin is a vanishingly rare event. It is a tiny fraction of a percent of the total volume of existence. This leads us to the perception-based heat theory. Some thinkers in the simulation community argue that heat is actually tied to observation. They point to the weirdness of quantum mechanics, where particles don't even have a set position until they are measured. If the building blocks of matter require an observer to collapse into a definite state, why wouldn't the energy of those particles require an observer, or at least a physical interaction, to collapse into a temperature? In this light, the coldness of space is a logic check. It is the universe's way of saying, there is nothing here for you to see, so I will not provide the energy. It is a systematic isolation that prevents the fire of the stars from ever truly warming the room of the cosmos. The stars are like high-intensity spotlights in a theater that has no air and no walls. You can see the light, but the room stays freezing because there is nothing for the light to hit. This challenges our very definition of what it means for something to be real. We assume that the heat of a star is a constant objective truth. But if that heat can only manifest when it strikes matter, and matter is almost non-existent in the cosmos, then heat is a secondary emergent property. It is a byproduct of the system, not the system itself. The system itself is the cold. The system is the void. The system is the unrendered blackness that stretches for trillions of light years. Imagine a universe that was actually hot. If space were filled with a medium that could hold heat, like a cosmic atmosphere, the entire sky would be a blinding, white-hot fog. The energy from every star would stay trapped in the medium, circulating and building up over billions of years until the entire universe reached the temperature of a star's surface. We wouldn't see the stars. We would be inside one. Life would be impossible. Complexity would be impossible. The very fact that space is cold is the only reason the universe functions. The cold is the heat sink. It is the exhaust of the simulation. By keeping the vacuum unrendered and cold, the universe allows energy to flow in highly directed, precise beams. This allows for render zones like our solar system, where complexity can emerge. We are like a small, climate-controlled room in a massive, unheated warehouse. The warehouse is dark and freezing, not because it's broken, but because that's the most efficient way to run a warehouse. You only heat the office where the people are. So when we ask why space is so cold, when the stars are so hot, we are looking at the interface between the data and the display. The stars are the data, raw, powerful, and constant. The cold is the empty space on the hard drive. And we are the pixels on the screen, the only place where that data is actually translated into the light and heat we call home. But this raises a final unsettling thought. If the universe is only rendering heat where matter exists, what happens as the matter itself begins to fade? As the stars run out of fuel and the galaxies drift further apart, the render zones will begin to shrink. The heat software will have fewer and fewer targets to execute its code upon. Eventually, the last atom will drift into the last void, and the universe will no longer have any reason to render anything at all. The simulation will return to its default state, a perfect, unrendered, and eternally cold vacuum. The cold we see in the night sky isn't just a lack of warmth. It is a preview of the end of the program. It is the nothing that was there before the Big Bang, and it is the nothing that will remain when the last spark of matter is gone. We are living in the brief, flickering moment where the nothing was forced to become something. We are the heat that shouldn't exist, screaming into a void that was never meant to feel us. But there is one more layer to this mystery. If the vacuum is truly an unrendered void, why does it still have a background hum? Why is there a minus 455-degree baseline that exists even where no matter is present? Is that the idle sound of the cosmic server? Or is it something much more terrestrial? A rare, protected exception that allows a world like ours to exist in the first place. To find that out, we have to return to the one place where the rules of the cold are broken, our own home. We have spent our journey looking at the universe as a place of extremes, a binary war between the furnace of the stars and the shadow of the void. But now we have to confront a reality that is far more haunting. We have to talk about the energy you cannot see, the fire you cannot feel, and the paradox that suggests the coldness of space is nothing more than a magnificent cosmic illusion. We call this the radiative isolation paradox, and it is the key to understanding why the universe is not actually empty, but is instead a raging, invisible sea of energy that simply refuses to touch us. To understand this paradox, you have to abandon the idea that space is nothing. We've used that word to simplify the vacuum, but the truth is far more complex. Imagine you are standing in a pitch-black room. To your eyes, the room is empty. It is cold. It is silent. But then you turn on a radio, and suddenly the room is filled with music. You turn on a cell phone, and it connects to a tower miles away. You realize that the room wasn't empty at all. It was saturated with invisible waves of information and energy. Space is exactly like that room. Every single cubic centimeter of the void is currently being flooded by the light and radiation of 2 trillion galaxies. At any given moment, 384 septillion watts of energy are screaming away from our sun alone, joined by the output of quadrillions of other stars. This radiation is everywhere. It is passing through you right now. It is passing through the spot where you would freeze to death. This is the invisible energy narrative. If you could see the universe as it truly is, if your eyes could perceive every wavelength of the electromagnetic spectrum simultaneously, the blackness of space would vanish. You would see a sky that is a solid, blinding wall of fire. There would be no gaps between the stars because the energy they emit fills every corner of the cosmos. The universe is not a cold room with a few candles. It is a room where the air itself is made of lightning. So we return to the central mystery. If the universe is literally drowning in energy, why does it feel like a tomb? The answer lies in the difference between energy and interaction. On Earth, we are used to energy being coupled to matter. When the sun's radiation hits our atmosphere, it has something to work with. It strikes a nitrogen molecule, and that molecule moves. It hits a water droplet, and that droplet vibrates. The energy is translated into motion, and we call that motion heat. But in the vacuum of space, the energy has no partner. It is radiatively isolated. The photons are there, carrying the potential to melt lead, but because they have nothing to hit, they simply pass through the void like ghosts. This is why cold is an illusion. Space isn't actively cold. It isn't a substance that is sucking the heat out of you. Space is passively empty. It is a system where energy exists in a state of perpetual transit, never stopping to interact, never slowing down to create a temperature. Temperature, as we've learned, is a property of matter, a measurement of how fast particles are jiggling. If there are no particles, the jiggling cannot happen. The energy remains in its raw electromagnetic form, invisible and unfelt. You could be standing in a stream of radiation powerful enough to vaporize a planet, but if you were made of the vacuum itself, you would feel absolutely nothing. This reframes our entire understanding of the cosmos. We think of the stars as the only active parts of the universe and the space between them as dead. But the radiative isolation paradox suggests the opposite. The dead space is actually the most active part of the system. It is the highway for all the energy in existence. The stars are merely the exit ramps, the places where that energy is forced to slow down and interact with matter. The cold we perceive is just the result of being in a place where the energy hasn't found a target yet. Think about the inverse square law. We know that radiation weakens as it spreads out, but it never truly disappears. Even in the deepest void between galaxies, there is light from 1 billion different sources overlapping and intersecting. There is more energy in that empty spot than in 1,000 lightning strikes on Earth. But because that energy is spread so thin and has no matter to interact with, it remains dark to us. It is energy without a medium. It is a fire without wood. This brings us to a deep existential realization. Heat is not a universal constant. It is relational. It is something that only exists when two things meet: energy and matter. Without that interaction, heat is a meaningless concept. This means that the universe isn't a place that is naturally cold. It is a place that is naturally isolated. We live in a world where we think of warmth as a basic right of existence, but in the grander context of the simulation, warmth is a rare, localized glitch. It only happens when the ghost energy of the stars is accidentally caught by a stray bit of cosmic dust or a lucky planet like ours. Imagine a high-speed train moving through a station at 200 miles per hour. If you are standing on the platform, you might feel a rush of air, but you aren't part of the train's kinetic energy. The train has an enormous amount of energy, but it is isolated from you. It only interacts with the station if it crashes. Space is the station, and the radiation from the stars is the train. The energy is moving past us at the speed of light, billions of tons of it every second, but it doesn't crash into the vacuum. It just keeps going. The vacuum is the only place in the universe where the train never stops. This is why our satellites and our astronauts experience such brutal extremes. They are the crash sites for the cosmic energy. When a spacecraft enters the sunlight, it is finally providing a target for that isolated radiation. The invisible energy finally has a face. It slams into the hull, and for the first time in millions of miles, it is forced to become heat. But the moment you move into the shadow, you are back in the isolation. You are back in the unrendered part of the room where the energy is still passing you by, but it has no way to touch you. The real mystery of the universe isn't why it's so cold. The mystery is how we manage to build a world where the energy is so perfectly coupled to matter that we can survive. We are living inside a thermal miracle. Our atmosphere doesn't just hold the heat, it forces the invisible energy of the sun to stay and talk. It traps the radiation and makes it bounce around, interacting again and again until the nothingness of the energy becomes the somethingness of a warm afternoon. When we look out into the night sky, we shouldn't see a cold, empty void. We should see a flood. We should see a universe that is absolutely saturated with power, a cosmos that is glowing with the potential of a quadrillion suns. The cold is just a sign of how efficiently the universe moves its energy. It is a sign that the vacuum is so perfect, so frictionless, that the fire of the Big Bang and the fury of the stars can travel for billions of years without losing a single degree of their potential. The cold is a mask. Beneath that mask is a reality of unimaginable violence and power. We are drifting through a sea of fire, protected only by our density and our distance. We are the rare outliers who have stepped out of the isolation, the ones who have forced the universe to reveal its heat. But as we look further into the darkness, we have to realize that the isolation is the rule, and we are the exception. The universe is a system of invisible energy, and we are the only ones who have learned how to feel the burn. As we move toward the final chapters of this mystery, we must ask, if the energy is everywhere, and if the cold is just an illusion of isolation, what happens when the isolation becomes permanent? What happens when the energy itself finally runs out of matter to hit? To understand the end of the story, we have to look at the ultimate winner of the cosmic war, not the fire and not even the energy, but the one force that ensures the cold will always have the final say. We have to talk about entropy and the day the universe finally goes quiet. We must now face the most uncomfortable truth of our cosmic existence. For thousands of years, we have looked at the night sky and seen a tapestry of light, assuming that the universe is a place defined by its stars. We saw those billions of nuclear furnaces and assumed that heat was the protagonist of the story. But as we peel back the layers of physics, a different narrative emerges, one where the stars are not the masters of the cosmos, but its temporary, desperate prisoners. This is the theory of entropy dominance, the idea that the universe's coldness isn't a problem to be solved, but the final inevitable victory of the void. In the language of physics, everything in the universe is tending toward a state of equilibrium, a point where all energy is spread so thin that no more work can be done and no more heat can be felt. When you look at the minus 455 degrees Fahrenheit baseline temperature that saturates every cubic centimeter of the vacuum, you aren't just looking at empty space, you are looking at the finished product. You are looking at a universe where entropy has already, for all intents and purposes, won. The cold is not the absence of a plan. It is the plan. It is the natural destination toward which every galaxy, every star, and every atom is currently racing. We often struggle to accept this because our perspective is so heavily skewed by our proximity to a heat source. We live on a planet where the sun provides all of our daylight and natural heating. We feel its scorching heat on a summer day and assume that this is what energy looks like. But this experience is a mathematical anomaly. The sun makes up 99.9% of the mass of our entire solar system, a staggering concentration of energy. Yet, the moment you move away from this singular, dense point of matter, you are immediately swallowed by an incomprehensibly large amount of nothingness. To understand the insignificance of the stars, you have to understand the scale of the gaps. The star closest to our sun, Proxima Centauri, is 4.3 light-years away. If you were to drive a car at 60 miles per hour toward that neighbor, it would take you 48 million years to reach it. In between us and that star is a distance of trillions of miles where there is nothing to catch the light, nothing to hold the heat, and nothing to break the silence. Expecting the stars to heat the entirety of outer space is akin to expecting a single bonfire in your backyard to heat up your entire country. It is a terribly impractical expectation that fails to account for the sheer volume of the nothing. The universe is not a room filled with light. It is a dark ocean where the lights are so few and so far apart that they can never hope to change the temperature of the water. This is the core of the entropy dominance theory. The idea that heat is a localized, fleeting phenomenon, while the cold is universal and eternal. From this perspective, the stars are not the permanent fixtures we imagine them to be. They are fleeting sparks in an endless void, momentary flashes of nuclear defiance that are destined to be extinguished. When we stargaze, we are literally looking into the past. Because light takes so long to travel across the vast distances of the vacuum, many of the stars we see in the night sky may have already run out of fuel. They may not even be alive anymore. We see the pillars of creation as majestic towers of gas and dust, but in reality, a supernova explosion likely destroyed them 6,000 years ago. We are looking at a ghost. This is the fate of every heat source in the cosmos. Whether they die in a violent supernova or slowly fade away as they exhaust their hydrogen, every star is a candle that will eventually flicker out. The universe is a system of isolated hotspots, tiny bubbles of activity like our solar system, wrapped in planetary atmospheres that allow heat to be absorbed and retained. But outside of these rare, precise exceptions, the default condition is the deep freeze. Space is not actively trying to be cold. It is passively empty, waiting for the temporary energy of the stars to dissipate according to the inverse square law. This law dictates that radiation weakens rapidly over distance, ensuring that the fire of a star can never truly touch the cold equilibrium of the void. Even the most stable planetary systems are not immune to this entropic march. We see chaotic systems where planets are pushed out of their orbits or even eaten by their central stars. We see galaxies that appear peaceful and stable today, but were once turbulent and non-chaotic in their early stages. Everything is in a state of flux, moving from the high-energy, high-heat state of the Big Bang toward the low-energy, maximum entropy state of the final freeze. The universe today is colder than it has ever been at any point in its history, and it will be colder still tomorrow. This reframes the entire story of our existence. We are not living in a universe of light and warmth that has a few cold spots. We are living in a universe of eternal, indifferent cold that has a few temporary warm spots. We are the fleeting sparks. The heat we feel is not the rule. It is the exception, a rare, protected glitch in a cosmos that is almost everywhere and almost always unimaginably cold. The entropy dominance theory suggests that the very existence of heat is a sign of imbalance. It is a sign that the energy has not yet finished spreading out. In this view, a burning star is a system that is still in the process of failing. It is a concentration of energy that the universe is actively trying to dilute. The coldness of space is simply the universe's way of reaching its goal. It is the state of perfect rest. As we look at the billions of stars in our own Milky Way, a disk of stars 100,000 light-years across, we have to realize that even this massive structure is just a thin filament of matter in a much larger void. The galaxies themselves are not randomly distributed. They are linked by dark matter into slender strands with massive empty voids in between. In those voids, there is no heat. There is no light. There is only the cosmic microwave background, the 2.7 Kelvin whisper of a fire that went out billions of years ago. This is the cosmic horror of the cold. It is the realization that the heat we rely on for our very survival is a temporary gift. We are huddled around the dying embers of a cosmic explosion, trying to keep warm in a cathedral that is quickly returning to its original frozen silence. The stars are not the masters of the house. They are the last guests at a party that is already over. When you feel the warmth of the sun on your face tomorrow, try to remember that you are experiencing a miracle of radiative coupling and atmospheric retention. You are feeling energy that has crossed 93 million miles of a vacuum that refused to absorb it. You are feeling a spark that is destined to go out. The cold equilibrium of space is not a threat from the outside. It is the fundamental truth of the inside. It is the destination where all things, from the smallest atom to the largest galaxy, must eventually arrive. We are living in the brief shining window between the fire and the ice. And as that window slowly closes, the nothingness of space is not just waiting for us. It is calling us back to the balance. The stars are hot and they are beautiful, but they are fleeting. The darkness and the cold that comes with it is forever. We have spent this journey exploring the brutal binary nature of the cosmos, a place where you can be cooked by a star's radiation while simultaneously freezing in its shadow. We have seen how the vacuum is an unrendered void, a silent highway for blind energy that refuses to manifest as heat until it strikes a target. But as we look back from the deep black toward that shimmering blue marble we call home, we realize that Earth is the ultimate cosmic anomaly. It is a rare, protected exception to a universe that is almost everywhere and almost always unimaginably cold. To understand the miracle of our existence, you have to realize that without our atmosphere, Earth would not be the lush, temperate paradise we know. It would be a bipolar wasteland of death. On Earth, we are pampered by a phenomenon we often take for granted, the lingering presence of warmth. When you step into the shade of a tree on a summer afternoon, the temperature doesn't instantly drop 500 degrees. When the sun sets, the world doesn't immediately plummet toward absolute zero. We live inside a thermal buffer, a thick protective blanket of gas that acts as a global climate control system. If you want to see what Earth would look like without this blanket, you only need to look at our nearest neighbor, the Moon. The Moon sits at roughly the same distance from the Sun as we do, receiving the same amount of solar radiation. Yet, because it lacks an atmosphere, it is a victim of the shadow contrast in its most violent form. On the lunar surface, if you are standing in direct sunlight at the equator, you are being hammered by raw radiation that heats the ground to a blistering 250 degrees Fahrenheit. But the moment the sun sets, or even if you simply step into the shadow of a deep crater, the temperature collapses. Without air to trap and distribute that energy, the heat bleeds away into the vacuum instantly, and the temperature plunges to minus 280 degrees Fahrenheit. This is the default state of a rocky world in the vacuum. It is a world of brutal extremes, where the difference between life and death is separated by nothing more than a shadow. But Earth is different. Our atmosphere, a thin layer of nitrogen, oxygen, and other gases, serves two critical life-sustaining functions. It absorbs and it distributes. When the sun's radiation strikes our atmosphere, the energy is not just lost to the surface. It is caught by 25 quintillion molecules in every cubic meter of air. These molecules act as a thermal battery. They absorb the blind energy of solar radiation, converting it into kinetic energy, motion, which we perceive as heat. Through the process of convection, this warm air rises and circulates, carrying energy from the sun-drenched equator to the frozen poles and around to the dark side of the planet. This is why, even at midnight in the middle of a desert, the air remains warm. The atmosphere is still holding the energy it collected during the day, acting like a giant circulating radiator for the entire planet. The most striking evidence of this atmospheric miracle is found on the planet Mercury. By the logic of distance, Mercury should be the hottest place in the solar system because it is the closest planet to the Sun. And during the day, it is indeed an inferno, with surface temperatures reaching 800 degrees Fahrenheit. However, Mercury has almost no atmosphere. Because there is no medium to capture and hold that radiation, the moment a patch of Mercury's surface turns away from the sun and faces the void, the warmth bleeds away as radiation at the speed of light. At night, Mercury's temperature collapses to minus 290 degrees Fahrenheit. Think about the absurdity of that physics. Mercury, the planet closest to the sun, gets colder at night than the surface of Mars, which orbits 3 times farther away. Distance from a star is only half the equation. The ability to retain and distribute that energy is what defines a world. If Mercury is the example of what happens with too little atmosphere, Venus is the warning of what happens with too much. Venus is the second planet from the Sun, yet it is actually hotter than Mercury on average. It is a world of runaway heat, where a thick, crushing atmosphere of carbon dioxide traps solar radiation so effectively that the surface never has a chance to cool down. On Venus, it is 900 degrees Fahrenheit day and night, from the poles to the equator. It is a planet-wide oven that never turns off. Earth sits in a Goldilocks zone, not just in terms of distance, but in terms of atmospheric density. We have just enough blanket to keep us from the minus 290 degrees Fahrenheit nights of Mercury, but not so much that we are crushed by the 900 degrees Fahrenheit furnace of Venus. Our atmosphere even performs a subtle trick with light that changes how we see our star. The sun isn't actually yellow, it emits light across a wide spectrum that would appear white to the human eye in the vacuum. But our atmosphere scatters blue light more efficiently than red, which is why we see a blue sky and a yellow sun. This scattering is a visual reminder of the constant interaction between radiation and matter that keeps us alive. Without this interaction, we would realize that we are living on a rock suspended in a minus 455-degree graveyard. The warmth we feel every day is a rare, precise, and protected exception. We are the only place we know of where the ghost energy of the stars has been successfully tamed, converted from a lethal stream of radiation into a gentle, circulating warmth that supports life. Our atmosphere is a shield against the void. It prevents our oceans from boiling away into the vacuum and prevents our blood from freezing in the shadows. It turns the unrendered environment of space into a rendered, habitable world. When you look up at the sky, you aren't just looking at air. You are looking at the armor of a planet. You are looking at the only thing standing between you and the eternal, silent freeze of the infinite. The miracle of the atmosphere forces us to reframe our entire understanding of the cosmos. The question is no longer why space is so cold. The real question, the one that should keep us in awe, is how in a universe this indifferent and this cold, a world like ours was ever allowed to exist at all. We are the glitch in the frozen simulation, a tiny pocket of vibrating warmth in a universe that is almost everywhere and almost always perfectly still. We have spent our journey through the cosmos looking for an explanation for the cold, as if the darkness were an intruder and the light were the rightful owner of the universe. We began with a question that seemed to highlight a massive cosmic failure. Why, in a universe lit by more fires than there are grains of sand on every beach on Earth, is the space between them so unimaginably frigid? We looked at the Sun, a furnace releasing 384 septillion watts of energy every second, and we looked at the vacuum, which sits at -455 degrees Fahrenheit, and we demanded to know why the heat didn't simply spread out to fill the room. But as we peel back the final layer of this mystery, we realize that our intuition has been leading us toward the wrong conclusion all along. The question isn't why the galaxy is cold. The real mystery, the one that should fundamentally change how you view your place in existence, is how there was ever any heat in such a cold universe to begin with. To grasp the magnitude of this shift, you have to look at the math of the nothingness. We perceive the Sun as the dominant force of our reality, but in the grand scale of the cosmos, it is a pinprick of matter in a sea of absolute void. The Sun makes up 99.9% of the mass of our entire solar system, yet even that massive concentration of energy is separated from its nearest neighbor, Proxima Centauri, by nearly 25 trillion miles of emptiness. If you were to drive a car at 60 miles per hour, it would take you over 48 million years to cross that gap. A gap where there is virtually nothing to catch the light, nothing to hold the heat, and nothing to break the silence. There is simply not enough matter and not enough hot stars to warm the entire universe entirely. The heat we see and feel is not the rule. It is a localized, high-energy anomaly that is desperately trying to survive in a system that is fundamentally geared toward the freeze. This is the revelation of entropy dominance. In physics, everything is tending toward a state of equilibrium, a point where energy is spread so thin that the dance of the atoms finally stops. When we measure the cosmic microwave background, the -455-degree whisper left over from the Big Bang, we are seeing the finished product of the universe. This baseline temperature is the only thing that is truly universal. It saturates every cubic centimeter of space, representing the lowest possible energy state of widespread radiation. Against this backdrop of eternal indifferent cold, the stars are not the masters of the house, they are fleeting sparks. They are temporary imbalances of energy that the universe is actively working to dilute and erase through the laws of radiation and the expansion of space itself. The universe is not actively cold, it is passively empty. This distinction is critical because it reveals that our experience of warmth is entirely relational. Heat is not a substance that exists in the vacuum. It is a byproduct of an interaction that occurs only when energy meets matter. Without a target to strike, a planet, a moon, or a grain of dust, the radiation from 1 trillion galaxies remains blind and unfelt. This means that the heat of the universe is actually a rare, localized glitch. It is a sequence of code that only executes when the hardware of matter is present to run it. For 99.99% of the history and volume of the cosmos, the heat software isn't even running. This leads us to a profound philosophical realization about our own existence. We live on a planet that is a rare, precise, protected exception to a cosmos that is almost everywhere and almost always unimaginably cold. We are wrapped in a nitrogen-oxygen blanket that allows us to absorb, distribute, and retain the energy of a distant star, preventing us from experiencing the brutal binary of the vacuum where you are either a furnace or a grave. Without this thin layer of gas, we would be no different from the Moon or Mercury, frozen in the shade and scorched in the light, a world of catastrophic swings and silent death. Our warmth is not a guaranteed property of our location in space. It is a fragile miracle of interaction. When you step outside tonight and look up at the stars, try to see them for what they truly are. They are not the light of the world. They are the last desperate protests against an encroaching and inevitable winter. Every star you see is losing the war against entropy, pouring its energy into a void that will never be warmed, a vacuum that merely watches the light pass through it without ever being touched by it. We are huddling around a collection of dying embers, living in the brief flickering moment between the white-hot flash of the Big Bang and the final absolute silence of the heat death. The cosmic horror of the cold is not that it is a force trying to kill us, but that it is a force that doesn't even know we exist. The vacuum is not cruel, it is indifferent. It is a system designed to move energy, not to hold it. We are the outliers who have found a way to catch that energy, to force the invisible energy of the stars to stay and talk for a while. But the nothingness is patient. It was there before the first star was born, and it will be there long after the last star has faded into a black cinder. This changes the narrative of our lives. We often feel small because of the size of the universe, but perhaps we should feel significant because of its temperature. In a universe that is almost entirely a minus 455-degree vacuum, the fact that you can feel the warmth of your own breath is a defiance of the highest order. You are a localized point of high kinetic energy in a graveyard of stillness. Your very existence is a temporary rebellion against the equilibrium. The real mystery of the stars is not why they can't heat the void, but how, in the face of such overwhelming nothingness, they manage to burn at all. They are the warriors of the light, standing alone in the deep freeze, each one a lighthouse whose beam will never find a shore. And we are the witnesses to their struggle. We are the ones who have turned the unrendered data of the stars into the physical reality of a sunny day. We are the miracle of the atmosphere, the rare exception that proves the rule of the cold. As we look toward the future, we know that the universe will only get colder. The expansion of space will continue to stretch the waves of the Big Bang, thinning the radiation until the baseline drops even further. The stars will continue to drift apart, their light becoming even more isolated, their warmth even more diluted. Eventually, the render zones of the galaxies will shrink, and the heat software will have fewer and fewer targets to execute its code upon. The universe will return to its default state, a perfect, silent, and eternally cold vacuum. But until that day, we have the fire. We have the brief, glorious anomaly of our own warmth. We are the glitch in the simulation that allowed a cold universe to feel what it's like to be hot. We are the survivors of the radiative isolation paradox, the ones who stepped into the beam and made it real. And as we drift through the indifferent and frigid cosmos, we carry with us the only thing that the void can never have: the memory of the heat and the courage to keep burning in the dark.